Logistic regression is a statistical modeling technique that is used where there's a binary outcome within a data set. So we're looking at data that can be described as pass or fail. Now there are some issues with the generalized linear model, which is the general framework under which logistic regression falls. We end up with a problem of separation, which is to do with being able to use one variable to perfectly predict the outcome of success or failure. David Firth produced a paper in 1993 looking at bias reduction for maximum likelihood estimation, and this has been applied to generalized linear models, but has been highlighted primarily as benefit for small data sets and logistic regression. So we're going to take a look at running logistic regression and bias-reduced logistic regression within R. So to do this, we're going to create a couple of dummy data sets. First one, we've got 12 points with a single explanatory variable x running between 10 and 40, and our pass we would set as, say, the 1 and fail as 0 for our response. So we see, except for at the ends, we've got in the middle bit, we've got a probability between 0 and 1. So in this case, we probably wouldn't expect it to be a problem with the generalized linear model function as is in R. So we run our GLM with our response variable and explanatory variable, as we always do when specifying a formula within the various modeling functions in R. So GLM for generalized linear model. We've got our data equals statement. This is telling R which data frame to look for when trying to pick out these columns, and family equals binomial. This is to let GLM know that we're fitting a model to binomial data, so binary outcome, and by default it goes for logistic regression. But there's also the option to do probit regression within this approach. So we save our model to an object so we can do things with the fitted model. So we run the summary function on this model. We can see that our estimate and standard error are not too unreasonable for the model fitted to this data. So let's look at the bias reduced version, which is in the package BRGLM, bias reduced generalized linear model. And the nice thing here is the only change we have to make to our code above is to write BRGLM rather than GLM. So we're getting a slightly different slope here for the two. We're getting standard errors that are finite and hence sensible for this data set. So then we might think, well, what do these two models look like? Are we getting something in terms of our curve relating our explanatory variable to the probability of success that's similar for these two, or getting something that's a bit different? So what we do here is we're going to create two data frames which are based on setting a range of the x value and then running predictions from this, so we get our curve response. So that means that it's between 0 and 1 for binomial data, and we're predicting across a set of x values within the range of our data set. So we do this both for GLM and BRGLM, so that's the slight difference we've got in our models, and then we put them together into single data frame. So I can plot this in ggplot2. It's Hadley-Wicken's Grammar of Graphics package. So we load that into our session and then run our ggplot function. So ggplot a data frame, so that's where our data is stored, and we're looking for columns x and y to correspond to the x and y axis. Color equals model allows us to separate out for a separate curve for these two fitting procedures, and geom_line is saying that we don't want dots, we want to join them together to get lines. So this is what the model looks like. Main characteristic, we can see we've got a slightly steeper slope for the GLM version than the bias reduced GLM, and this is quite a common feature if we fit these two models to the same data set. So with our second data set, we're going to put in some separation. So we've got our perfect not passing here and passing there based on our x value. So if we then fit our generalized linear model, we see we're getting these very large standard errors. So this is not a particularly sensible fit to the data. So up pops our BRGLM, fit through the same thing, and here we're getting a more sensible slope and standard error out. So we're now getting a model that we probably can have a bit more confidence with. So the question is, do these two also look different in a similar way to our first data set? So we run the same thing to put the fitted curve for GLM, BRGLM, put them together into a single data frame, and run our ggplot function. So here we can see now the bias reduced version gives us this nice smoothish curve, but we're getting this almost step function for the GLM, which is highlighted by the problems we had with the maximum likelihood estimates and their standard errors.